So we'll talk about audition, body senses, and chemical senses. Please don't go out in the world and tell people you only have 5 senses, because you have more than that, right? So we've already talked about vision. That was awesome. We'll talk about audition. Hey, how many of you love your vestibular system? You all should. How many of you like to know that you're upright and or not spinning around in a circle? Pretty important. So vestibular system. You've got a ton of somatosenses, right? So these are things that tell you where your body's located, different parts of your body, if your body's moving, touch, tickle, itch, pain, hot and cold. Gustation, that's taste, and olfaction, that is smell. All right. Basically, like this giant chunk of your brain is all devoted to sensory systems, and it's pretty important. I love this first line here. Left it on there from the publisher. We hear sounds. You guys didn't know that. You've made it a couple decades in your life, and you don't realize we hear sounds. I know it's a real shock to you. Any of you are so overwhelmed by that, you need to leave. I understand. It happens to everybody. Basically, what happens is an object's going to vibrate. It's going to cause those molecules to move. These molecules move pretty quickly, 1,200 kilometers per hour, somewhere around 335 miles per hour. This is the speed of sound. I am required by the state of West Virginia, since I'm an employee of the state of West Virginia, to say the name Chuck Yeager 3 times at this point in the lecture, since he was the first guy to break the sound barrier. So that's once. I'll say Chuck Yeager again, and then finally when we wrap up, before it's all said and done, we'll briefly talk about the Bell X1 and how Chuck Yeager just was super fast. Met my contractual obligations. They're not going to fire me this semester. These vibrations happen somewhere, maybe 30 to 20,000 times a second. We measure that in something called hertz, right? So 1 vibration per second is 1 hertz. 10 vibrations per second is 10 hertz. Whatever. Here you go. This is awesome. Here's a speaker, right? You have this compressed air and then air that's sort of decompressed or rarefied that eventually comes into your ear. This big guy out here is called the pinna, your outer ear. The pinna is awesome. It does some really cool things. Some of you use it to hold up glasses. You stick earrings in there. That's great. The other amazing thing it does, it actually funnels sound into the rest of your auditory system. So it's there for a reason. Don't bypass it, right? I am going to enjoy my life a lot more in probably 15 years when all of you lose your hearing because you've been using earbuds. And I haven't, because I'm always an over-the-ear guy. That's the way it should go. I've been telling people for years, like, earbuds are a bad idea, right? Evolution gave you a pinna, you ought to use it. Steve Jobs gave you something to cram in your eardrum. I don't know if that's a good idea, right? Are you going to trust the millennia of evolution, or 25 minutes of Steve Jobs thinking about how you're going to listen to your iPod? I don't know, right? So there you go. So you really should send things through here, not jam it in there, right, and bypass that whole process. So I've been telling people this for a long time, Scotty, and then when it was like an article published like 2 years ago saying that you guys are going to be the first generation to lose your hearing before people who are older than you. I thought it was hilarious, and I laughed. None of you could hear me, but I laughed, and so I thought, well, that's great. So if I see you in the future, sometime like a decade or so from now, I'll wave and scream, so you'll know that it's me. You won't have to yell back, because I'll still be over the ear. So if you can, switch to over the ear. I promise you it's going to be better for your life. Okay? So you've got your pinna. Sound waves come in there. They start banging around on that tympanic membrane or eardrum. They're going to vibrate things called your auditory ossicles, also known as the inner ear bones. Those are pretty awesome. Right? You got 3 of those. They punch around on the cochlea. We'll talk about that in a minute. All right, pitch. Right? The higher the frequency, the higher the pitch, right? So if it's a high frequency, we're thinking Alvin from the Chipmunks. If it's a low frequency, we're thinking Barry White. Okay. You guys don't know Barry White, you're missing out on a lot of social activities. Loudness is the intensity of the sound wave. Timbre is kind of cool. If we have a sort of a basic tone, right, it's going to be one sine wave. It's just going to be this nice smooth sort of frequency, not a big deal. Most natural sounds are not like that. Most natural sounds look kind of jagged, right? They're still repeating, but they're jagged. They might have the same frequency, they might have the same amplitude, but they're going to sound different, right? So Tiffany, I think you said you were a musician, right? You probably play the, I'm going to take a wild guess, the bassoon and the piccolo. Those are your chosen instruments for today. The point is, pick whatever two instruments you want. You can play the same note, the same frequency, at the same amplitude, but they're going to sound different, right? A trumpet and a saxophone, I assume, can both play a C sharp at 85 decibels, right? But most people are, if you don't know it's a saxophone and a trumpet, you'll at least know it's two different instruments. They're going to sound like they're making the same frequency, the same pitch, but it's two different instruments, right? And that's because of all of these fun little, complex waves riding on top of that main wave. And there you go. There's an awesome diagram showing those sort of three qualities of sound waves. All right, here's the rest of your ear. You've got that tympanic membrane. These are your auditory ossicles, the malleus, incus, and stapes, right? That's basically to take that sound wave, take it from air, and leverage that so that we can beat around on the cochlea. The cochlea is full of this sort of gelatinous material, right? How many of you have ever skipped a stone across the surface of water, right? That's exactly what would happen if we didn't have these ossicles in here. The sound would come in and it'd bounce right back out, right? So we just kind of hit that change in media right from air to that sort of jelly substance, and it bounced right back out. So we have those inner ear bones to leverage that, to add a little extra force. Okay. Then we send those vibrations out through the cochlea. We're going to activate some cells out there sensitive to different frequencies. Boom, we're going to fire action potentials, and you know what you're listening to. Talked about all of that. Inside your cochlea, you have inner hair cells. These are the guys doing transduction. Okay. They're taking that vibration and turning it into an electrical signal. The outer hair cells are doing something called gain control. You don't have to worry about that too much. If you get really excited about it, great. Read on it on your own. What's kind of cool about the cochlea is the way that it's structured. Sort of from start to finish, there are different frequencies, right? So as we are close to one end, it's going to be high frequencies, and as we get to the other end, it's going to be low frequencies. We call that organization tonotopic, okay? Because it's mapped out in an orderly fashion across frequency. When we were thinking about the visual system, everything we did followed a map of the visual world. So we called that sort of retinotopic or visuotopic, right? Things that were next to each other in the real world were next to each other when we translated that to our brain. In this case, frequencies, let's say that's like 2500 hertz down to 100. We're going to follow an orderly progression. So, this is kind of cool. We should talk about tip links. These hair cells have cilia that come out, sort of stacked like this. In between each of these, we have these links, right? And they're each holding onto an ion channel. And when those hair cells, those cilia are moved on those hair cells, those tip links become taut, and they rip open those ion channels, and ions come in, right? Previously, we'd only talked about opening ion channels using neurotransmitters, right? But now we're actually using that mechanical shift, right, that deflection, to open those ion channels. It's pretty awesome. All right, and so here you go. This is a zoomed in view. Previously, I'd always told you it's going to be sodium coming in, right? Here's another sort of weird example. Caveat to that, it's going to be sodium or calcium. I'm not going to ask you, but just be aware of that. When that force is going in the right direction, rip open that ion channel, in come those positive ions, and guess what? We cause an action potential. When we talked about the visual system, we went retina, LGN, V1, and that was really the end of the story. We did some fancy things up there. The auditory system is a mess, and it's a much more complicated system. The reason for this is because information from your left ear and information from your right ear, we need to compare those two, right? We need to compare the time that they arrive. Most of you have a head that has some width, right? If you don't know this, you can get out a measuring tape and go, well, my head is this wide. Your ears are that far apart. Because your ears are a certain distance apart, sound coming from one side or the other is going to arrive at a different time at each ear, right? We can use that information, that time difference, to tell us where that sound is located, where the source of that sound is, right? So if something hits your left ear sooner than your right ear, even if it's just a millisecond or a few milliseconds, we know it's going to be shifted to the left. If it's the other way, we know it's shifted to the right. So we need to take information from one side and compare it to information on the other side, and it creates a whole bunch of crises and crosses there before we get up into the thalamus and the auditory cortex. Not a big deal. So there's this whole sort of extra subcortical business going on that you don't need to know about. Here's that nice tonotopic map. That's the cochlea sort of unrolled. As I said, we start with higher frequencies on the end here closest to that round window, and out here we have lower frequencies out at the apex. Okay. This is because of the structure of the cochlea. This end is stiffer, so it doesn't. It's not as flexible, right? This end is more flexible, so it's going to vibrate at a slower frequency or lower frequency. Don't worry too much about auditory cortex, just know we have a primary auditory cortex. Here's a kid with a cochlear implant. I don't know if any of you are familiar with those. They're kind of interesting. They actually bypass the cochlea completely, right? So they use a microphone to collect sound information. They take that sound information, and instead of going through the pinna and into the cochlea, they go into the auditory nerve. So this guy collects sound information, transduces that sound into an electrical signal. Because we know about that tonotopic map of the cochlea, and we know that the auditory nerve follows that same pattern, we can figure out which fibers in that auditory nerve are for high or low or mid frequencies. We can put, we can send those electrical signals into the right part of that auditory nerve. So it's kind of a cool process. Things are getting a lot better in terms of the software that handles these translations, right? So folks who have cochlear implants now versus, let's say, 10 years ago, they actually have a much more natural sound than what they did in the past. It's still not the same as someone without a cochlear implant, but things are getting better. It's pretty cool, right? Don't worry about that. We already talked about spatial location. Okay, that's kind of cool. Let's skip over this. Complex sounds. Don't worry about that. We do integrate visual and auditory information. How many of you have ever heard a noise and you turned around to see where it was? It's pretty exciting, right? That you can do that. There are also all kinds of weird sort of like optical and auditory illusions, right? Where you will you'll have a video clip of someone making a sound, making some sort of syllable, and you'll hear a different syllable, right? And then what you sort of perceive as something in between. It's kind of interesting. How many of you have ever watched in like dubbed films. Anybody watch a foreign film that's been dubbed? It's difficult, right, Tyler? Because you're like, wait a minute, that almost looked like he said what he said, but no, it's not. I don't know, it's difficult to, if anybody's like, I don't know, Clint Eastwood or Bruce Lee fan, you watch some of the older work, right? Anybody spaghetti western fan? Nobody's for a few dollars more. It's disappointing. You need to take about 6 hours of your life between now and next week and watch the Man with No Name trilogy. Then you need to take like another 6 hours of your life and watch the films by Akira Kurosawa that inspired those. So it's only like 12 hours. It'll be worth it, I promise. 5 or 6 good films there. Instead, you're probably going to go home and watch like YouTube clips of, I don't know, like dogs running off of steps or something. I don't know what you do with your time. This is what I imagine you do with your time. Don't correct me if it's wrong. Hey, who remembers that time, and I hope you do because it was just like 15 minutes ago, when I said there was a what and a where pathway for vision? Would you be surprised if I told you there was a what and a where pathway for the auditory system? I hope not, because it's right here on the slide before I talked about it. So a little preview. There's a what and a where pathway still following that same sort of dorsal and ventral organization, right? So that what and where, or where versus what, dorsal versus ventral, still works, right? And we think about it with the auditory system. It's important to know what the noise is and where it is, right? So if you hear a car, that's awesome. You need to know it's a car. But you need to know where that car is too, right? Because that can change your movements and your motion. How many of you love music? Right? We established that some people do, some people don't, whatever. There are different brain regions involved in that. I'm not going to think about that too much. Okay. Questions about the auditory system? I'm not going to ask you a whole lot about that, obviously.
And the tip links with the action potential, is that a graded action potential, or that's just an action potential?
Yeah, it's just going to be an action potential. Because we're going pretty quickly right into the auditory unit to get that action potential on into those cortical regions. It's a good question. All right, vestibular system. This guy's located pretty close to that cochlea, right? You've got sort of two major sections here. You've got your vestibular sacs and your semicircular canals. These guys are really important for balance, making sure your head is always upright, and adjusting eye movements, right? So that's kind of fun. You can test these things out. We do this all the time, I'm certain. So in between those dog videos while you're waiting on that advertisement to go through, you probably spin around in your office chair really fast, right? And then you stop yourself, and the world still seems to be spinning but in the opposite direction. That's a vestibular system sort of illusion, right, Aspen? I mean, you've seen other people do it, not you. What's happening there is your visual system is saying, hey, we've stopped, but your vestibular system still is getting some input, right? And because those two systems are not matching up, you have to sort of average that, and you're trying to reconcile that experience. And to do that, you tell yourself you're moving in the wrong direction. It's kind of fun, right? Has anybody not experienced that? Okay, I assume most of you had it. So those are semicircular canals. Vestibular sacs, these are awesome. They tell you about gravity. How many of you are familiar with gravity? Yeah. Happens all the time, right? And that's awesome. So the vestibular sacs will tell you which way is down, right? How many of you have ever experienced vertigo? Yeah. So that's when, again, your visual system says, that way's down, but your vestibular system said, I think that way's down, right? And so because you're getting two different sort of sets of information about which way's down, you're trying to reconcile that. It really causes some problems. Hey, who wants to hear a story about sloths? I'm going to tell you one anyway. So this is cool. So, if I were to bust open all of your heads, right, and we might try this later, Bears. If we were to pull out their vestibular organs, what we would find is that there's very, very, very little variation, right, between these semicircular canals in humans, right? Humans are a fairly mobile, acrobatic species, right? We move pretty quickly through our environments. We're actually one of the best, as we already established, one of the best runners in the animal kingdom. I know, again, there's that caveat about the cheetah. That only works for 3 seconds, though, right? If you want to run longer than that, be a human. So we move, and we move around and do different things. So not a lot of variation in the structure of our semicircular canals. You can imagine some of the detriments someone would have if their vestibular organs were really out of line with the norm, right? They would have difficulty with balance, they would have difficulty walking, difficulty moving through their environment. That'd be really, really problematic. So we move pretty quickly. Now, if you're a species that's not very fast, right, like a sloth, you can actually afford to have some variation in your vestibular organs. And in fact, sloths have a pretty good amount of variation in the structure of their vestibular organs. Again, they're not moving fast. What happens if a sloth falls out of a tree? It's eaten, right? It doesn't have to get back up, right? So that's a pretty good life, right? You fall out of a tree, just wait. Someone's going to eat you. Don't even bother to try to get back up. So that's kind of the life of a sloth. So they can afford to have this sort of variation in their semicircular canals and so forth. Humans, we can't, right? Because we're constantly moving through our environments and moving quickly, so we need to have really good vestibular organs, and we do. So that's awesome. Now the vestibular organs are full of that same endolymph that's in your cochlea, and they also work pretty similarly on these hair cells, so they're going to move and deflect those cilia in very much the same way, using tip links and so forth. Again, it's going to be that mechanical opening of those ion channels that's going to cause action potentials down the, in this case, the ampullary nerve, but through those nerves. There's a slightly different setup in your vestibular sacs. You actually have these things called otoliths, right? That's really awesome. It means ear stones, right? So you've got sort of these like calcified substances in there sensitive to gravity. Gravity's going to yank them down or yank them in one direction or the other, and they're going to then deflect those hair cells. Okay? That way you know which is down. Now there's some interesting things you can do with, and there's actually, this is from a frog, I think. Yeah, it's from a bullfrog. Let's see, the hair cell from the sac here. Some interesting things you can do in terms of vestibular organs. We've talked about some of those. There's also what we call nystagmus. I don't know if you guys are familiar with this. So it's when your eyes kind of move really fast to one side or the other. If you find someone who has sort of ingested more alcohol than they should have, and you put them on their side, not on their back, but on their side, their eyes will actually start to move, right? So they have these kind of weird eye movements. And that's because, again, they're getting different information from their vestibular system than they are from their visual system. Alcohol has an interesting tendency to get in that endolymph and change the density of it, right? So things are going to move through it at a different rate than what you're used to. And because that happens, you're going to be sort of have some balance issues. Not exactly know which way is going to practice. Makes a lot of sense now, right? All right, you've got some cranial nerves, not a big deal. All right, we should talk about somatosenses, right? So soma means body, so these are sort of body senses. You have cutaneous, and it's going to be skin, so we think about like touch, tickle, itch, some pain, temperature, hot, cold, things like that. Proprioception, that's a fun one. How many of you can't see your feet, but you know where they're located? That's because of proprioception, right? How many of you have ever moved your body and didn't have to watch every part of your body move, but you knew it was moving? That's called kinesthesia, right? It's pretty awesome. Otherwise, we would all be like looking down as we walked, and that would be problematic. You'd be running into walls all the time. And then there are what we call organic senses, right? And these are not things that didn't use pesticides, right? These are the senses that come from your inner organs. Sometimes they're called visceral senses, right? How many of you know the concentration of hydrogen ions in your blood? Well, you don't have to. There are sensors in your body, receptors that monitor this, right? And they'll make adjustments one way or the other. They'll trigger things to happen to adjust that concentration as you need, so you don't develop like acidosis or something. Okay? So you've got those organic senses. You're not typically consciously aware of that, right? Blood pressure is another one. How many of you know you have a blood pressure? Great, Autumn. Well on your way to some medical profession, I can tell. You have a blood pressure. Great job. But you probably don't know what that is. It's not, I'm going to say largely, it's not important if you know what it is at all times, right? You should probably know what it is periodically. But there are cells in your body that are measuring blood pressure and making adjustments as best as possible. Pain sensitivity, we'll talk a lot about that later. Later we'll talk about endogenous opioids, right? So you do make opioids inside your body to release those when you feel pain. Not too big of a deal. Here are a bunch of different receptors that are embedded in your skin. I'm not going to expect you to memorize these. What I do want you to get from this is that because we're talking about different kinds of sensory experiences, right? Pressure, vibration, tickle, touch, hot, cold, pain. We need different receptors for each of those different types of stimuli, right? And that makes perfect sense. You don't want something that's going to be sensitive to pressure is not also going to be sensitive to cold, right? You're going to build those differently, and that's really what I want you to take out of that. You don't need to know all these different names or specifically what they are. This is kind of a nice diagram that shows you, things down here that are encapsulated. They're sensitive to pressure. Things that are closer to the surface, especially like free nerve endings. Those guys are going to be sensitive to pain. Makes a lot of sense. Something that's causing pain, you don't want it to have to stab you really deeply to recognize that it hurts, right? But you also don't want like a fly to land on your, I'm going to try to draw a fly. I don't want a fly to land on your arm and you think like somebody dropped a brick on your hand either, right? So if you want something sensitive to pressure, probably put that a little deeper, wrap that in some sort of encapsulation. If you really want to read that chart, you can. There it is. Again, we talked about touch, vibration, temperature, pain, and itch. Those are always fun ones, right? Somatosensory pathways, I'm not going to ask you which direction those are going. There are two kinds of temperature. There's obviously warm and cold. These actually use free nerve endings, so the same kind of nerve endings that carry pain information. How many of you have ever felt something so hot or so cold it caused pain? Okay? That's pretty standard. So when you get on the extremes on either one of these, you can actually start to perceive that as painful. Things that are painful, pain typically equals tissue damage, right? Something that is too hot or too cold can cause tissue damage, so it makes a lot of sense to register that as pain. Don't worry about those too much. And that's a bunch of stuff about pain that we'll think about later. Phantom limb is kind of interesting. I don't know if you guys are familiar with phantom limb. There was a guy a number of years ago, V.S. Ramachandran, who developed a sort of an interesting, unique solution to phantom limb pain, right? He created this box with a mirror inside of it, so if someone had lost one of their arms, they would stick their other arm in, and then they would see a reflection of that, right? And then they could kind of perceive that they had that arm. This is similar to the rubber hand illusion. Anybody familiar with the rubber hand illusion? Fun one. How many of you volunteer for the Brain Expo? That's coming up soon, right? Yeah, that's a fun one, right? I usually do the rubber hand illusion. So basically what you do is you have a rubber hand, it's a fake hand, and then you have like the kid's real hand. It sounds really weird and creepy, but you take a paintbrush and you rub it on their hands. Right, so you can see why that sounds kind of strange. Like, hey, send your kids over to Marshall, run a paintbrush over your kids' hands. But we rub the paintbrush over their hands for a while, and then eventually they'll start to feel the paintbrush out on the rubber hand, and not on the real hand. And if you really get a kid into it, which can happen sometimes, you can go and kind of smack the rubber hand, and then they'll like pull their hand back like they think they're going to feel some pain, which is kind of fun. No, it sounds torturous, but the kids get a lot out of that. Trust me, there's like this real light bulb moment that happens. So I guess I should make the announcement. When that comes around, I will announce it. It's usually in March, right? Does that seem accurate? October, March, I don't know. It's one of those months, and you get a free t-shirt. And peanuts. There's usually peanuts. It looks great on resumes if you're wanting to go to graduate school, right, or get a job. One of those things.
What is it? Just like,
When?
what is it?
Oh, it's really actually pretty cool. So they usually take the Don Morris room over to the Student Center, and they'll bring in, I think last year, like almost 800 kids that were like 3rd through 5th graders, 2nd through 4th graders. They're kids that are still little and dirty, but they're not so little that they can't go to the bathroom on their own. Right, so they're somewhere in that age range, and they'll bring them in, and you teach them about brain science, right? So they come around, there are like 30 different stations maybe, where you can teach them different things about brains. It's pretty exciting. The kids usually like it. It's cool when you see the same kid come in, like consecutive years, and they're like, oh, I remember this from last year. I'm like, well, that's great. Didn't waste my time. All right, we're not going to worry about this. We'll talk about the pain later. Oh, hey, placebos are awesome, right? I know Megan's sister's really into the placebo effect. This is one of my favorite. This is one of my favorite diagrams here. So the placebo effect is actually real, right? So if I give you something to tell you, hey, this will make you feel better, guess what? It'll probably make you feel better, right? And that's how placebos work. But this study went a step further than that, and they actually gave folks like a pain reliever, but it was a fake pain reliever, total fake. And then they started shocking them, right? This is so much fun. So you give someone like, here's a pain reliever, take it, you won't feel any pain, and then I'm going to shock you. And so then you get a shocker, which is exciting. They had two groups here though. One group they said, hey, this is like a low price pain reliever, right? It's on sale. You guys are getting a good deal on this, or we got a good deal on it. And then the other group, you said, whoa, man, we really paid a lot for this expensive pain reliever, right? It wasn't on sale. The folks who thought they got the expensive pain reliever, which again, totally fake, said that it actually worked better than the folks who thought they got the discount version. That's pretty amazing, right? I don't know. Just makes you think about, I thought it was kind of interesting. I think about like marketing, right? Those folks, they'll tell you like, oh, this is a really high-end, expensive thing. Put it in like a shiny box. Probably the same thing you bought in some other box, right? Just tell yourself, I don't know, maybe you can alternate, like if there's someone else who does your shopping for you, like save fancy boxes from one time you bought something, and then like cram, I'm thinking about this, right? Like cram the cheap stuff in there and go like, hey, look at this. I mean, obviously you would know if you did the shopping, but if someone else does it for you, it doesn't matter. I thought it was fun. Placebo effect, there you go. Oh, hey, what about gestation? We should talk about that briefly. This is when you taste things. In order for you to taste something, here's a real shocker, it's got to be in your mouth. I know nobody was ready for that. You've got to dissolve whatever those molecules are in your saliva and have that activate those receptors on your tongue. There are really only a handful of qualities of taste, right? We've got salty, sweet, bitter, sour, right? Umami is a fun one. I mean, savory. Then you also have spicy. Don't worry about this receptor business. Those are your 5 basic tastes. What's interesting about this is each of these tastes are actually governed or originate from a sort of a particular chemical, right? And so if you think about this, what's an easy one? Saltiness, right? I mean, what are we looking for there? Salt, right? Nobody was, particularly sodium. Sweetness, we're thinking about things like glucose, other sugars. Sour, we're really looking for hydrogen ions, right, which make things acidic. Bitterness are going to be plant alkaloids. Most things that are bitter are poisonous, right? And finally, umami, we're looking typically for things like glutamate, right? like amino acids, okay, because they're going to have that savory. So if you think about how many of you are familiar with monosodium glutamate, MSG, right? You guys are probably like, oh, I got to avoid MSG, it's going to kill me. The sodium in it probably will. The other parts probably aren't going to do anything to you, so don't worry about it. Just try to avoid sodium, you'll be fine. You've got taste buds on your tongue.
Are there really like taste regions on your tongue that deal with
No.
this specifically?
No. You've got a tongue, it looks something like this. I'm not, and then you got like teeth down here, I don't know, I'm not, I didn't study medical art, right? Somebody had broccoli for lunch and they didn't brush their teeth. No, your tongue, you can taste everything everywhere, okay? Yeah. No, I know they'll try to tell you like, well, you can only taste sour back here. I'm like, well, no, that's wrong. I don't even know where they are, so I'm just like making things up. Where do they tell you sour? Anybody know? It's wrong. You can taste sour all over this. You can taste sweet all over it, whatever. Doesn't matter. Here are your taste buds, right? So you've got inside of these papilla, right? It's just like the surface of your tongue. You've got taste buds in here. Each of these taste buds is made up of multiple taste cells, right? So each of those taste buds has in it, Megan, cells for salty, sweet, sour, bitter, umami, right? So in those taste buds, all of those cells are included in it. So not only are there not taste regions on your tongue, there aren't really even taste regions within your taste buds because your taste buds contain all of the taste cells and taste receptors that you have. Don't worry about this, that's going to be confusing. All right. Now, previously we had talked about vision crossing from left to right. I didn't tell you auditory system crosses left to right. Gustation does not, right? If it's on the left, it goes back. It really seems kind of like a waste, right? I mean, your tongue's right in the middle of your head anyway. Why would you bother switching things? The other interesting thing is there's not any cortical organization for your taste, right? So if you were to try to figure this out and you think, oh, well, I'm going to map this tonotopically like I did with, you know, different frequencies. That made sense because you're going from high to low frequencies. What do you do with taste? Like, is salty closer to sour than it is to savory? I don't know, right? That doesn't make any sense. So it's all just sort of mixed all over the place, right? It's not a big deal. Don't worry about too much of this. We should talk about olfaction briefly, right? You have olfactory receptors. Guess where those are located? Up your nose. Again, really telling you things you don't know, right? You have the olfactory epithelium up there. These guys constantly make new olfactory cells. One of the few places in your brain as an adult that you're constantly producing new cells, right? The other being the hippocampus. It is a chemical sense. The other chemical sense was gustation, right? Because we were testing for chemicals. These are probably the two, probably olfaction was taste was probably the first sense to develop, right? Because you're kind of floating around in this like water, right, substance or whatever, you dissolve chemicals in there and you can kind of test, or you can detect those, right? This is probably the first sense to develop, and we added things later. What's interesting about the olfactory system is you only have about 1,000 different types of olfactory receptors. And that sounds like a lot, right? Until I tell you you can identify 10,000 different odors. Okay? So that's pretty impressive, right? 10,000 odors. What's interesting about that is, so how do I go from 1,000 receptors to 10,000 odors, right? It's all about sort of population coding and combinations, right? So if you have a particular odorant, whatever that is, it's not going to activate just one receptor. It's going to activate multiple receptors in a particular pattern. A different odorant activates a different set of patterns, right? So it's very much like, how many of you have one of those bike locks, right, that you spin around? It's got like 4 digits, 0 through 9. You have one of those, you're familiar with those kinds of locks, right? Those kind of barrel locks. You've really only got 4 positions. And you've got 0 through 9, so you got 10 numbers each one. You can make almost 10,000 different combinations, right? Different numbers on that, which is really something interesting on one level, and maybe sort of frightening on the other if you have one of those kind of locks. There are only 10,000 different, patterns someone could try and they can steal your bicycle. So you think about how long that takes to try each pattern, right? You do the math. Probably within an hour, somebody could have your bicycle stolen if you're not watching, right? Think about that. If you've got nimble fingers. Jacob, sometimes I think about stealing their bicycles. So, there you go. Mitral cells, you don't have to answer this, but is anybody Catholic or a fan of chess? I know those are like two things that you might not think go together, but they both involve bishops, right? And bishops wear mitre hats. So they kind of have this, right? That's kind of like the top of them. It's not like the worst thing I've drawn. So it's a bishop. Your mitral cells, they're shaped kind of like mitre hats. That's why they're called that. All of those olfactory cells, they'll kind of funnel into the mitral cells, and then from there go into your olfactory cortex. All right, we already talked about those odors. Oh, we do send a lot of odor information to the amygdala and the hippocampus, right? We can smell things and we can know if we need to be afraid of that. If you're a rat and you smell like cat urine, boy, that's something that should probably get you excited, right? You should probably run away from that. Most of the time where there's cat urine, there's a cat. I don't know if you guys recognize. All right, so here you go. These are your olfactory receptors down here. Here are your mitral cells. Each mitral cell is only going to receive information from one type of olfactory receptor. That's all happening up here in the olfactory bulb, and then we're going to go on back into your brain for other sort of processing. Here's what I was trying to tell you earlier about that coding of olfactory information. So if you have a molecule such as this one, look how it activates these two receptors. That's pretty cool. Here's another molecule that's completely different. It activates, there's a little bit of overlap there, but it also activates a different receptor. So it's a different pattern of activation. So we know that it's a different odorant. Questions about that? Great.
Olfactory also does it.